So thank you all for coming. It's amazing to see this many people in this small room. I hope I give a good talk, and if you have any questions, just put them on Slido. We can then talk afterwards. I'm also going to be around the next couple of hours and tomorrow morning, so you can ask questions there. So who am I? I'm Marc Lemburg. I'm from Düsseldorf in Germany. I have a consulting company doing Python projects. And I've been active in the Python community for quite a number of years. I've also used Python for quite a number of years. I'm old, so as you can see. I don't want to go into all these details. I've done lots of stuff. Let's get started. So, motivation. So let's say you have a startup, right? So you have this crazy new idea that you want to put out there. Of course, you need to start thinking about what's going to happen if suddenly, next day 100,000 users start coming to your website, and you need to be able to handle that load. So you need to have some idea, at least, of where you want to go. You have an initial idea, but you need to prepare for the future. So when you start architecting your solution, you have to really think about how you can grow, how you can add flexibility to your architecture so that you don't develop into some kind of rabbit hole, so that you can easily scale up later on. And basically, there are many ways of how you can do this. I'm going to talk about one way to do it. It may not necessarily be the right way for you to do it, so basically you have to figure out whether this is a good strategy or maybe some more classic strategy would be better to use for this. So of course, a lot of people know probably about REST and GraphQL. It's like the go-to architecture that you would probably use nowadays. If you use microservices, then most likely you're using REST for this. REST it's a very strong following. It has lots of support on the front end. It has lots of support on the back end. So there's lots of technology to choose from. There's one catch with REST, though. It's very inflexible when it comes to changing data and to changing your schemas. So if you want to change a schema and to do that often, then every single time you make that change, you have to roll out a new release. You have to change your front end. You have to change the back end. You might have to change the way that you scale your application. So it's not necessarily always ideal. And this is where GraphQL comes in. GraphQL basically makes it possible for your front end to query exactly what it needs to make. If you want to make a change to your backend, you want to have more data in the backend, then you can just change the backend and then have GraphQL dynamically adapt to that. And so it's better, like the better option instead of using REST. But both have the problem that they're hard to scale. Now let's have a look at a not so new architecture, actually, the event-driven architecture. Event-driven architecture is something that is actually quite old. It was very much in the news in the early 2000s. It was called SOA at that time, or at least that's what the industry called it. And well, back then, there were two architectures, essentially. One was web services. Web services at those days used mostly XML, so SOAP. And then later on, it turned to REST and JSON and so on. The part about the event-driven architecture kind of got forgotten, though, in the subsequent years. And I want to kind of, put this out there to perhaps have a look at it again, because it's actually quite a useful system. So one of the first things that you have to know about event-driven architectures is always asynchronous. So there's nothing synchronous. You don't call out to something and then expect to get a result back right away. It's about events. So basically, you issue an event, you send out a message, and you expect some message to come back to you, and then react on that message. It scales very well, as you can imagine. I mean, if you basically decouple everything, then you can just add more workers, and then you have a more scalable system. And it also allows you to be very flexible in terms of architecture. So let's say you want to change part of your system because you find that it's not really performing that well, or maybe you want to change the architecture of one part of your system. then that's very easy to do because you're only communicating with messages, and so the other systems that use your subsystem, they will not really have to know how a subsystem that you want to talk to is actually implemented. So let's have a closer look at this. Event-driven communication is basically the heart of this architecture. So what you do is you send around messages all the time. You have producers that create messages. You have consumers that consume the messages. And in between, you typically have a broker. A broker takes care of making sure that the communication actually works. And the most critical part in this architecture is actually this broker. So when you choose a broker, you have to be, really have to dive into the details and have to figure out whether that particular choice that you made is a good one. What's interesting here is that the consumers can, of course, also produce messages. So it's not just going from left to right. You can also go the other way around, or you can have like circles. So you can have communication going back from the consumer to the producer again to get, for example, feedback done. The events themselves are organized using topics. So this is essentially how you make sure that the right messages go to the right consumers. And there are various ways of how you can use these topics to organize your system. So what is encapsulated in those messages? Typically, it's about things that have happened. It's about change in state, for example, that happened that you want to tell someone about. It can also be used for initiate commands. For example, you can say, okay, please start this, let's say, a job run that you want to do in your workflow system. The messages themselves are very similar to what you have in web messages. So you have headers and you have a payload. You have to be very careful to keep those messages small because the throughput of your whole architecture depends on how many messages you can process per second. And so it's usually better to put all the bulk data, the like huge payloads, you put them somewhere else and just reference them in your messages. So how do you encode the data that you want to keep in those messages, have on those messages? The typical way to do this is using Apache Avro, which is the default for a very popular broker called Kafka. How many of you know Kafka? Most of you? Okay, excellent. Kafka today is mostly used for actually processing data. So you have data pipelines, which are actually very similar to this kind of architecture, except that the data that you're processing doesn't actually execute anything. It just gets processed, right? So it goes in and then gets processed and goes out again. Whereas in this architecture, everything is flowing around, right? So you have lots of communication going back and forth in your system. But of course, there are other protocols as well. Protobuf is a very popular one. MessagePack is another very popular one. You can also use JSON. You should always be careful to make sure that everything is typed and ideally also signed so that whenever you put something into your system, something new, then you make sure that the messages that you're actually getting and you're processing are coming from the right other partners. And this is very important because ideally you want to have this a zero trust kind of system and architecture. In order to keep everything nicely handleable and small, you can use a compression algorithm. zlib is very popular. Snappy is a bit more efficient, so that's something that you can use there, and the brokers typically support these as well. I also already talked about the topics. So topics are sometimes also called channels or queues, depending on which kind of broker you're using. Topics organize the way that information flows through your system. So a topic could be, let's say, I have an order coming in, and I want to process orders. So you call that topic, you call it orders, and then you have a producer producing these topics, these messages in that topic, sending those to the broker, and then you can have consumers that hook up to the broker and then take those orders and initiate some action based on that. There are two ways to process these things. One is called pub/sub. How many of you know pub/sub? Okay, few. So basically this is about publishing and subscribing. it's very much like what you do, for example, on Twitter. Let's say you follow someone, then you're subscribing to a feed, and the person that you're following there is basically providing the publish part. So what happens is whenever something new comes in, a new message gets generated, you get informed about this new message, and then you can react on that. This is a very, very simple approach. It works very well. It scales very well. There's one downside, though, because if you're not always listening to the subscription that you have there, you might lose some messages, and that, depending on what kind of message you want to process, that may cause some data loss. So there is a second way to do this called streaming, which works a bit differently. So it's not about publishing and subscribing, but instead the broker keeps, say, a list of the last, let's say, 100 or 1,000 messages. And then when you use the streaming approach, the consumers can actually go into that stream and also have a look at what were the 100 last messages that were published on that particular topic. And you can then access that. And you can use this to do some kind of replay, for example. Or if you want to join in later, or let's say you have a system that works on mobiles and the mobile is disconnected from the server, then the mobile, when it gets connected again, it can go to that stream and then get the messages. So what's very important here is that you have a decoupled system, so the senders don't need to know anything about the consumers. The consumers don't need to know where a message is coming from. So you have this ideal state of separation of concerns, and everything is encapsulated. So your processing is really the subcomponents that you have in your system are really isolated from everything else, and you can very easily make changes in that kind of architecture. So these are some message brokers. I just put a few here. There are lots and lots more. The most popular one probably is Kafka, but there are also other ones that are used in the industry. For example, AMQP is used a lot in finance. MQTT is used a lot in IoT. You always have multiple implementations that you can use. I put all the open source ones here. Then, of course, if you're going to the cloud, you can get these services there as well. So Google pops up, Azure pops up. In AWS, it's called SNS. And of course, you can also use a Kafka in AWS as a managed service. So these are things that you can use. These are brokers that you can use. But like I said earlier on, you have to be careful with the choice of the broker that you're using. And these are the things that you have to be careful about. So one is the guaranteed delivery of messages. So you want to be sure, at least in some cases, that when you put a message into a queue, it actually gets processed at some point. And this is very important because network failures can happen. There can be data loss. You can have failures in your system. A subcomponent in your system may go down, and then when it comes up again, it needs to then reprocess everything that's in the queue. So that's something that a broker should handle for you. Another very important point is making sure that the messages only get processed once. Because let's say you're in Amazon or you have some kind of web shop system and an order comes in. Of course, you want to process that order only once. And there are various modes of operation of these brokers that make sure that these things actually work. Something else that's important is the trade-off between message size and performance. Like I already said, you should probably keep messages very small. They should ideally fit into a network packet. So if you put something out there that has like 100 or maybe 1,000 bytes, then you're pretty safe, and that can be handled very well. You can scale up to hundreds of thousands of messages per second if you want. So that's very much possible. And I already mentioned the failure modes. If something breaks, you want to make sure that whenever the system then comes up again, everything continues processing. And that's also a very nice thing about this architecture. Unlike web services that use, for example, a REST interface, and you have a microservice architecture. In a microservice architecture, you have to basically be able to handle these failure modes yourself, and you have to program yourself. In this architecture, basically the failure modes, they are handled by your broker, and it's much easier to implement these things. Right, so we talked a lot about the architecture. Now, of course, you want to document whatever you're doing. You want to tell everyone in your company about the events that can happen, and the consumers, they also want to publish what they can consume. So just like you have with REST, there is an API standard. In REST, it's called Open API. You probably know. Maybe if you don't know Open API, it's the same as Swagger. In the event-driven architecture, there is a new standard. The standard got developed or started, the development started in 2017, so it's fairly new. It's called Async API. Unfortunately, Python doesn't have a good story there yet. And that's one of the reasons why I'm doing this talk, because I think that we need to do something about this. We need to have more packages, more support for this kind of architecture in Python. Right now, it's basically just Node.js and Java, right? So enterprisey stuff that's using this. But I think we should really put some energy out there and then get more support in Python for this. So let's do a quick recap. Event-driven architecture. On the right here, I put a kind of a typical system that you have. This would be an order system. As you can see, there's a REST backend in there as well. So it's very well possible to combine these architectures. So you can have a client to talk to a REST backend, and then have the REST backend initiate the events, and then send the events into your architecture that you have with components. And then have an order manager ideally manage everything, so make sure that the orders actually go through. Right, I'm not going to talk about all of these things. The slides are already published on Discord, so you can go there and download them. So let's just do a quick example here. I already talked about the web shop and the orders, so I'm just going to use that as an example. In a REST system, what typically happens when you order something, then the order comes in, then you have to do the payment stuff, you have to do fulfillment, you have inventory that you have to handle, you have to queue everything for actually doing the delivery later on. So all of these things have to be done synchronously. You always have to go into your system and call out to these subsystems directly when the order comes in. And that, of course, creates a lot of problems if one of these subsystems is not available, and can easily then crash your system, or give a bad UX, because the user will probably then expect the order to go through, and then actually it doesn't go through. So the architecture helps a lot. The EDA architecture makes this a lot easier to handle, and it can make sure that these orders actually do go through. Another important thing is when deploying things. Because whenever you make a change in here, you will very likely have to make changes throughout the whole system. You have to deploy the complete system again. Let's say you're changing something in your inventory system, maybe a schema there, right? Then everything else will have to know about the schema change as well. And this is a lot better in the EDA kind of structure, because everything is decoupled. You're only sending messages. You only have to make sure that the messages can actually handle whatever change you make. And it's very likely that this will not happen often, that the messages can stay the same, but the implementation that you have for the subsystem can easily be replaced by something else. So the system is a lot more scalable. The code management in there is a lot easier to do. Deployment is a lot easier. And this is the main reason why, for example, Amazon is using this architecture for doing all the order processing. They started with a REST system. They had a monolith system early in the 2000s. And then they realized they couldn't scale that system up. And also going for microservices didn't work, because they needed to scale so much. And they had all these issues that I talked about with subsystems not working sometimes. And so what they did is they basically re-implemented everything using this structure. And as you can see, it's giving them a good success. So what about Python and the architecture? We do have async support in Python, and there were a few talks about async at this conference. So we are actually in a very good position to do these things, especially if you want to do pub-sub kind of interfaces. Very easy to use. What's not so great is the Async API support. There are a couple of modules that you can use, but not that many. And the Async API community, the community that's actually building the spec, is also not very Python aware. It does have some support for it, just very basic support in this Async API Studio that allows you to build these spec definitions. But it could use a lot more. Likewise, if you go to PiPi and want to find some packages, normally when you go to PiPi, there's always lots to choose from when you have a problem, right? But in this particular case, there isn't much to choose from. And what's worse is that the support for these things has more or less stopped. So we could really use more efforts in this kind of area to make it easier to use this kind of structure. What you can do, of course, and lots of companies, of course, are using this, is you can go low level. So you can just take your broker and interface directly to the broker, let's say a Kafka. I put some of these PiPi packages up here that you can use for these kinds of brokers. There's definitely a lot there. Also for the cloud services, I didn't put them up here. So it's very easy to go with this low-level kind of approach. If you want to go a bit more high level, you can also use packages like Broadcaster, for example, that abstracts a bit away from, from the direct broker access. And then you can replace, for example, a Kafka with a Redis, or maybe you can use Postgres, the pubs up in Postgres if you want to have something that's smaller. Maybe you want to run it on your notebook, which then, is installing Kafka is a bit more difficult. And so you can use those, or you can just basically go basically Python all in. There are some implementations there that basically try to have the complete broker written in Python, and you can play around with those maybe while you're developing things. But that's pretty much it. So there isn't really a whole lot. And while the architecture is really useful and really something that you should consider if you're starting your next big thing, we do need better support for EDA in Python. Right, and that's all I wanted to say. Main takeaway is, as always, never stop to learn, always try out new things, and look outside the window to find new technology out there, new ways of doing things, even if they may not necessarily be straightforward or straight away to implement. Right, thank you.
Thank you very much. So we have a couple of questions. Can you open a bit on how to do the signing of JSON? How it's laid out in a nutshell?
The messages are actually, you can actually use existing technology for this. So you can basically use the same technology that you have for SSL processing that you have on the web. You can use that. So it's very straightforward to implement that. You can even use TLS for the network layer if you like.
Okay, great. It seems like EDA seems suitable to work with data lineage. Is that right?
Sorry?
It seems like EDA seems suitable to work with data lineage. Is that right?
It is, well, lineage basically, data lineage basically is about you know where things are coming from, you know where things are going and how are they being processed. So yes, it does help a lot with that because the messages actually carry that information for you. And if you like, you can use, for example, the meta information that's in the headers of these messages and store them away, maybe in a log server, and then use them later on to basically figure out where a certain message came from, where it went, and how it got processed.
Okay, great. Next question. What are good resources to study more about event-driven architecture?
One go-to place is this Async API organization website. I don't have a URL here. I think in the slides, if you click on the Async API mentioned there, then I think that's a link. I can post some links to the to Discord later on.
Okay. Next question. Your company does consulting. How are devs' reception to the EDA's idea? How do you prevent accidental hybrid architectures and ensure idempotency is implemented?
That is a very good question. So this architecture is not that well known yet for doing larger scale applications. So there is some training that you have to do. You have to make people aware of it and maybe try out things on a smaller scale first, and then get them into this. In terms of preventing a hybrid architecture, I don't think that you actually need to prevent this. Like I said, you can easily combine REST with an EDA architecture. You just have to document the interfaces between those two worlds in a good way. And this is where this Async API spec actually helps a lot, because it defines what your messages are all about, where they're coming from, what the consumers will have to do with those messages. And you can also define which consumers there are for a certain type of message, right? So all of that is basically in the documentation, and it's automatic because it's machine readable, very much like Open API, right? So you can actually have a website where you go, or you can have a system in your knowledge base that takes these specs and then generates documentation from these specs.
Okay. Next question. Any best practices on dependency discovery between services and on event schema migration besides versioning?
Well, discovery, again, this is Async API, right? So basically, this is the go-to place where you publish everything. And this is also how, because it's machine readable, this is how your subcomponents can figure out what's there, what's available. And the second part was about versioning, right? So
yes, and on event schema migration besides versioning.
Event schema migration. This is interesting. I have to check. I read something about the Async API not supporting versioning, but maybe I've just misread that. I'm not sure. You can go to the Async API website and look it up and see whether it does support versioning or not. In general, what you can always do is if you want to have a new version of a message, then you can just create a new message type that you then start using. And of course, you can keep the support for the older versions of that message type in your system so that you don't have to always upgrade everything at once, but you can do it gradually and then deploy things step by step.
Okay. What problems have you faced in debugging a Kafka unexpected behavior, for example, in case of a rebalance?
This is hard, to say the least. I mean, it's because everything is asynchronous. If you've ever done asynchronous system programming, you probably know that things can go left and right, and it's just a complete mess to debug. So, what you have to do is you have to very much take care that your system allows observability, so that you need to do lots and lots of logging. You need to store all these logs somewhere so that they're easily accessible. So for example, on AWS, you'd use CloudWatch for that. You push all your messages there, and then you need to have a good query language that can actually help you put together everything in order again. Because it's async, everything is out of order, right? Well, normally at least. And so it's very hard to track everything. There's one good thing that you should keep in mind. You should always try to have things like request or order IDs in your messages, so that you can easily correlate the different messages to one, let's say, the original event that triggered a whole lot of other events that happened. That makes things easier. And if you have subsystems, it also makes sense to use these IDs for the subsystems, so that you can basically put everything together again, and you get a whole tree of messages that were generated, and you can then follow up using that and use it for debugging. But it's hard, definitely. that is one of the downsides of the architecture, I must say.
Thank you. Our time is up now. Thank you all for joining. Thank you, Mark.